All right, so today we're going to talk about light. We've already talked about waves, and then we talked about sound, and we're going to revisit some of the concepts that we talked about in our wave unit. We're going to address why objects appear the way they are. And the second half, which we'll get into this tomorrow, we will go back and look at your light ray lab and talk about convex, and concave lenses, and convex and concave mirrors, and the effect they have on this light, our light rays. So when we talk about light, we are talking about everything on the EM spectrum. All right, so if you think back to the EM spectrum that you drew in your notebook, as a matter of fact, I'm going to turn to that. Turn back to your EM spectrum. Which spans from your TV, FM radio to your gamma waves. Now in our wave unit we kind of addressed all of these in general. This unit we're going to specifically talk about our light sliver, okay, our visible light sliver. So at what wavelength is that? Give or take. Bless you. To the -7. Okay? So that is our wavelength for our visible light. So we are going to be just focusing on that rainbow. Okay, our Roy G. Biv. Now, humans, as most mammals, as all mammals, have evolved to see visible light. Now some have evolved a little bit more sophisticated vision than others. We as humans, we have evolved to see color. So when light hits our optic nerve, our brain decodes that frequency and we see different colors with the help of our cones, right? Rods and cones. And we've grown up learning which frequency is named what color. So when we see a green object, and we've been taught to say green for that frequency. Same with blue and the rest of the colors. But it is basically just a frequency of light that we are looking at. Or more importantly, that is coming into our eye. So our Roy G. Biv, which is our acronym for our rainbow, which if we look it down at the bottom here, we have our spectrum of visible light. On the left side we have our red, and on the right side we have our blues. Okay, so reds are low frequency, long wavelengths, and blues are high frequency, short wavelengths. So let's talk about why this matters in something that you use probably pretty frequently. DVDs. If we were to look at a DVD, we'll have a side view, okay, and this is going to be a vast oversimplification. Okay, we have inside we have these pyramids. Okay, these pyramids are what hold the information. Okay, hold the data on the DVD. This layer on the top here is a clear plastic layer that protects your DVD. Okay. Well, DVDs use red lasers. All right, and as that red laser comes down, it reads it almost like a record player, and with grooves. Right, and that's how you get your picture. Well, recently, relatively recently, in the grand scheme of things, what's the new format?
Blu-ray.
Blu-ray. So if we take that same Blu-ray discs can have more than twice the amount of data, because what is special about blue light? It has a higher frequency and a shorter wavelength. Okay, so now this laser, this blue laser, can read much smaller bits of information. So that means you have a higher density storage, which means you have more pixels, which means you have a sharper image. Okay? And then, as you guys figured out yourself, that's why they're called Blu-ray players. Okay? Because they use blue lasers.
So only difference is the picture is clear?
The picture has more information. So it has more pixels, and the more pixels you have, the sharper it is. So here, I'll give you an example. A very crude example. But I'm going to say that we have a DVD player with 9 pixels. And another one with, how many is that? 81? Sure, I'll go with that. So if we were to make an image, okay? You have this many pixels available, and I'm going to make an O. Okay, letter O. I have no option but to make a square letter O, right? Alright, well, with Blu-ray, since I have much greater pixel density, I can make an O. Oops. Pixels out of whack. That looks more like Oish, is that what you said? It looks more oish. Okay, it looks more like a circle because I have more pixels. Same thing if you take a picture with a 1 megapixel camera, okay, and it's all blurry versus a 10 megapixel camera, which is very sharp, that has 10 times the amount of pixels in the same area. So it's just about, I mean, it's the same concept as Atari games. Okay? Atari, those are 8-bit systems. Okay? So you'd have 8 bits. So it was very blocky. Okay? Whereas, you know, you go through Nintendo,
16.
and then Nintendo's 64,
3-dimensional.
and then it just ramps up from there. So where now you have, you know, 3D accelerated graphics where there are millions and millions of polygons made out of billions of pixels. So you get a 3-dimensional environment. I mean, you look at even the first 3-dimensional games come out, like Wolfenstein 3D and Doom, and how crazy pixelated those were. But still, I mean, it was mind-blowing at the time because it was no longer a 2-dimensional, like Super Mario Brothers, side-scrolling platformer. It was a 3-dimensional actual maze, first-person view, going in 3-dimensional space. I mean, it was mind-blowing at the time.
And then Super Mario 64. Yeah. All over. Right.
Alright. So, going back to light. What's the speed of light?
29, 97, 92, 28.
That's a big.
3.0 times 10 to the 8 meters per second. That's right. Or if you want to be a little bit more exact.
999.
I was right.
There you go, Max.
I can read numbers.
Reading. I'm proud of you, Max.
Remember that in 1 second, light can approximately travel around the Earth. How many times?
7.
7.5 times.
Oh, I know that.
And what is our unit? And what is our symbol? Symbol is C. What's Einstein doing over there?
Equals MC squared.
But what did he go through first?
Velocity squared. Equals MA squared and MP squared. He forgot. So he's gonna go to the next one. E equals
I get it.
See, it would have been funny, but we didn't know, so. What? What?
And another thing to remember is that light rays, they travel in straight, parallel lines from the source.
Just got
He went through A and then B, and then he finally got to C. E equals MC squared.
Well, it all kind of rolls together. Yeah.
Well,
E equals MC squared.
how you
Just
get
pulls off.
E equals M.
That's not good, Trayvon.
How funny.
Guys, please, the comments. Put your filter on. Alright, so we've already talked about this. Okay? Well, let's talk about color and why things are the color they are. Now, whenever we're talking about color, you have to remind yourself that we're talking about light. Okay? We're not talking about watercolors or oils or paint of any sort or art. you're talking about light, because you confuse the two, which people will do inevitably, they're backwards, as you'll find. Okay, they're opposite each other. So, white light. Anyone know what white light is?
All
Absences are.
All colors.
Oh, okay.
Okay? Which you demonstrated in the lab, right? When you took a prism and you separated white light into all the colors. Your rainbow. Right? That's what you did. So white light, and that might be a good idea after white, put light there so you don't forget. Talking about white light. It's a combination of all colors.
This was
So-
the appropriate class past white sky.
Actually, that would have been appropriate 2 slides ago. Why is the sky blue?
Because of the pollution and
Because of the
The way
pollution.
the way the sun's ray like gets racked off the atmosphere.
Okay, so if we went back and looked at our spectrum, right? Why isn't the sky red? Yeah, because blues, the high frequencies and short wavelengths, they are the higher energy of the light. So when light is refracted through the atmosphere, blue is the result. Yeah.
It's one of those sunset.
well, that when it it gets red.
So yeah, I mean, once it gets close down to the horizon,
Losing it.
there's more particulates and such, dust and smog and pollution, and as a result, you get those reds and purples and pinks. Everyone have the white?
Yes.
Okay, so black.
That's why. Man, no color. The color is.
Black is the absence of all light. Okay? Brings me, what is the significance of this picture? Who can tell me with their hand raised? Hand raised. Max, what do you think?
Well, there's no force, so she's falling, so there was no, I don't know.
Is it because she's still on black chair and there's nothing there?
Okay. Okay. Do you have
Black, like attracted to the black.
closer? So we start off with nothing there.
Black
We got down black chair, which is good. We went to it's hot.
He's sitting on the sun.
I don't know what
Because it's absorbing all the light that
That's right. So
Oh, I didn't know.
we have to be careful when we're talking about this, okay? Black absorbs, right? Black doesn't attract light. I mean, that's one of those things you don't think about when you're saying, but think about it. It doesn't have a sign of sunlight over here, or it's not like a bee going to a flower.
It's not giant.
Yeah, it's not sucking it in somehow. It's just when the light hits it, it is absorbing all of the light, and then what happens to it?
Just go to the
Turns into
heat.
It goes away. Then we have conservation of energy means that it has to be transferred to something and it converted to heat. And then to the woman. Yes.
That looks like sacred. Let's get the car.
White is absence of it's showing.
And then it's hot.
So the heat waves in that next picture, the asphalt or concrete
Looks like
is getting heated up, right? It's really hot. As a result, it's heating the air close to the surface, and you're starting getting those heat waves, which is basically showing the expansion of the air, and the air is rising as it's getting hot. Yes.
So if it was white, they would be.
Yeah, we can do that.
If the ground was white, yes. But at a certain point, it won't matter because this ground will still heat up to a certain temperature. It just won't be as dramatic. Which is interesting because if you think about, white versus black, houses, the roofs, shingles on houses are what color? They're dark, right? They're dark, charcoals and blacks and grays. But when you think about it, that's counterintuitive, right? Why do you want a bunch of black tile on your roof?
So it doesn't go straight through.
But it will absorb all the heat.
The heat inside doesn't escape.
So when it snows, it's already hot.
Well, a place like Oklahoma, where we barely have a winter, why do we want black roofs?
So inside the house when it gets hot.
To keep the shingles together.
It'll heat up the attic and it heats up the entire house. Why do we have black shingles? Is there any reasonable reason?
Probably not.
Keep the heat out.
No, it's just aesthetic reason because it looks good.
Oh.
That's it. It has nothing to do. If we had common sense, all of our shingles would be white,
Okay.
right? Because that would reflect the sun. Yeah, even better, mirrors if it didn't, blind.
Helicopters.
Yeah. So if we had white shingles, that would reflect all the sun, or reflect a lot of the sun's rays. It would not heat up your attic as much, which then would not heat up your house. We spent so much money on making our attics insulated for that very reason, and having attic fans and basically ridge lines that has flow from the soffits on the edge, because we're trying to cool the attic, because the attic is the number one reason why your house is hot, and therefore you have to use a lot more energy to cool it, i.e. your air conditioner. But it's basically an aesthetic reason.
So we're just gonna eventually just all switch to white shingles.
It would make sense.
But they would get dirty.
They would get dirty.
Dirty? Well, bird poop is white too, right? Blend right in.
Only bits of it. Just saying, maybe.
If you guys have been inspecting bird poop, is that what you're telling me?
It's on my good shit.
Alright, so when we're talking about an object of a specific color, it means, depending on what the color is, that means that when white light hits that object, then that object is going to absorb all of the colors except for the color it is. And you always have to keep in mind that you're not going to be able to see an object or see the color of an object unless that color reflects into your eyeball.
So one color.
So if we were to have a green plant, okay, say it's a tomato plant. Tomato plant in the sun. That tomato plant is absorbing what colors?
Everything was green and red.
Oh, and red.
If there's fruit on there. Say there's no fruit at all. Say it's just a tomato plant.
All colors green and
Right.
brown.
So it's going to be absorbing Roy Biv, right? And it's going to be reflecting G, or green. Now all plants do this. All green plants do this because what they do is they have evolved to use specific frequencies of light in their production of glucose. Through what process? Photosynthesis, of course.
Yeah.
So these green plants absorb Roy Biv to produce glucose and reflect green, and that's why they're green. Now, a lot of grow rooms, they will have red light in there, red frequency light, because plants really like red light. So what about this? What happened if you were to have a plant in a room with no windows with just green frequency light on that plant? What would happen?
It would die.
It would die, right? It would look nice and green for a little bit, but over time, because it will not be getting in, it would be the same thing as just putting it in a closet. Okay? It would just be reflecting that energy. Moving on.
No.
So we're going to have a practical example of this with a green turtle
So, where is the screen turtle?
hanging out in the next slide.
Oh, I thought it was here.
So like, okay, so this wouldn't happen with like a piece of paper, right?
Piece of paper is white.
No, like a piece of like red paper.
Okay, it's red paper. What is it doing?
It's like anything but red. Okay, so it goes for anything.
Goes for everything. Your shirt, what is your shirt reflecting?
Everything but a little bit.
That's right.
But why does it look?
Green turtle. So if we have our white light hitting our green turtle, what's happening? Green's reflecting, right?
Okay.
And it's absorbing everything else.
It's gonna be hot to the turtle.
What? I don't know why that turtle just did that. Yeah.
So does it work for like your eye color? So can you change it? Or like just looking at the color?
No, because the pigment in your eye is only reflects whatever color it is. Now, when we're talking about reflecting and absorbing colors, you know, we're really oversimplifying this a lot because we're talking about specific frequencies. And in nature, in reality, rarely do you get a specific perfect frequency. We have a mix of frequency. That's why there's, hundreds of greens. If you've ever gone to Home Depot or Lowe's and gone to the paint section and looked at the colors that they have, I mean, there's 500 different colors of green. It's ridiculous. And they're all named something different, which is, I find, even more funny.
How did they change
Green number.
I don't know, they're like tropical forest.
tropical bananas?
Yeah.
So, okay, have you ever been to Home Depot and you see them mix your color for you?
Yes.
So why do they put all those colors in there?
That's right. So, I mean, all colors, pretty much they're working with their blue, red, and green. Okay? So those are your primary colors that they're taking, and depending on how red you want it, or how green you want it, or how blue you want it, all of those are percentages.
It's like RGB.
Okay? Which combined, they will get you that perfect color. And if you want to see another example of that really quick,
Yeah,
like RGB, like
no, but I'll show you if we look at,
you're gonna show some of the colors. 10 colors.
actually, yeah. So if we go to colors, more colors, custom. So this is more what we're talking about, our different red, green, and blue. Okay? So this tells you your value, your red value, your green value, and your blue value. And depending on how you change these values will determine what color you actually end up with. Okay, so if I increase this red color, you see it's making it lighter because this is moving it closer to the red. Everyone see that? It's making this cursor go over and this cursor go over as I go up. It's getting more red. Where if I want more green, it goes the opposite way. I'm all the way up to blue. Go down blue. Goes down that way. See it curving?
Whoa.
See? So parabola. Okay?
That apple.
Okay, so let's talk about filtered light. Our turtle's back again for more.
Oh yeah.
Well, I don't think you can
Do you have a name for the turtle?
Timmy.
Oh yeah.
I thought it was.
So what happens if we shine red light, red filtered light on our green turtle?
He eats it. Yep.
What do we get? What happens? What's reflected?
Nothing.
Blue is green.
Everything but red.
Everything's reflected.
Purple.
Okay, well hold on. We're not thinking about what's going on here. We only have red light.
Okay.
There is no green. Red light's hitting the turtle. What's reflected?
Nothing.
Blue.
White.
Wait, no.
White.
Not one.
Be black, wouldn't it?
Nothing reflected.
Nothing's reflected. Why?
Because turtle can only reflect green light.
Oh wait, no. This is not reflecting. No, we're reflecting.
What does the turtle do with red light?
Keeps it.
Absorb, keeps it, absorbs it. It absorbs red light because it's green. It absorbs red light because it's green.
So if it was red
So-
and a green light came in, it would absorb the green.
Yes. And what color is the turtle going to look now?
White.
Stay
Black.
green.
Red, brown.
We guessing.
The turtle would look black
That's close.
Whoa, that's
because no light is reflected. No light's reflected, so it's going to look black.
oh, wow, that's creepy. So if you see like a turtle, how would that happen?
So if you put a red turtle in a room with just red, it would turn black.
It would look black.
Oh, cause red vision, everything is black.
So that means that, and the turtle didn't have to be green. Turtle could be yellow or blue, and it would still look black under a red light. Okay? So what if I have another example? Say I have a red room, okay, completely red. Ceiling's red, walls, floor, red.
Oh my red.
It's your room, Javon, I don't know.
I'll be tricked out.
There's a red table. On the red table there is a green turtle.
Yeah.
That turtle going to appear black.
And I'm going to turn green only on. Green lights only.
Oh,
Turtle will be green, everything else will be
everything else will be black.
Turtle would be green, everything else would be black.
Oh, that's awesome. Cool.
Try it out.
Alright, let's talk about Snell's law.
I really want to do that.
Snail. Is that your real name?
I have a feeling you
Snail?
have animated snail on the slide.
No, I don't.
You don't,
No.
but
Unfortunately not.
I can clearly see you do that. You snail running across the bottom of the slide or something. Yeah.
Now, we know when light travels through a substance, its velocity is affected. Raise your hand if you know how it is affected. It's affected by two ways.
Wait. No.
How is the velocity of light affected when it travels through a substance in two ways? Number one, Ethan.
It changes direction.
Changes direction. That's right. That's just our refraction, right? And it does.
It gets bigger.
I'm not saying hands raised. I'm saying some random. Anyone else? Anyone else? Max, what do you think?
It gets bigger?
It gets bigger. No.
Everything.
Oh, say the right.
That would be refract.
Say it.
That's
No, you should.
Devin, what do you think?
Devin, you should know.
I'm guessing it changes its frequency.
No, come on.
No.
Is it like if it goes through something else?
Come on.
It goes to, just like we did with the lens.
Yeah, something's like.
What else? Matt. Come on, something. But you had it. It changes direction and Kate. It slows down. Yes. That's the whole reason why it changes direction, right? Because it does slow down.
And that's why all light goes through.
Now, the amount it does slow down is due to the object's optical density. Okay, whatever it's traveling through, the medium it's traveling through has a density. The amount that the speed or that velocity is reduced is due directly to the optical density, which is letter N, lowercase n. So, with this being said, what is the relationship between velocity of light and density?
Inversely.
Inversely proportional. As the density increases, the velocity decreases. Which brings us to our equation.
Wait, no.
Not yet?
Speed, I don't know, velocity. You have a shorter thing than velocity in the substance. There's nothing.
V. But I wanted to write it out so everyone knows.
So it's like 7 different velocities.
So what is our N again? Optical density. So density equals, what's C?
Light.
Speed of light divided by velocity of the light in a substance. Okay?
Yeah.
And it's the optical density.
Optical density, yeah. So using this equation, we can figure out how much light slows down in an object. Now, it should be pointed out that the object has to be able to allow light to travel through it, right? We're not talking about a solid object here that is like steel.
Exactly.
Okay, it has to be transparent or translucent.
I was just thinking about that. I was like,
I was trying to think of what I was like, fluorescent.
how is supposed to slow down going too long?
Okay, copy all these optical densities down. You'll be referring back to this. And if you do not have enough room at the bottom of your page, just go to the next page. Do not try to squeeze these in the bottom because you won't be able to see them.
Really fun.
Mainly because it's ineffective.
Oh, this Henry's really loud. Maybe doesn't do anything.
So, what is your equation you're going to use? What's your equation?
N equals C over B.
Yes. So, when we look at this, let's make our equation triangle. What goes where?
C goes on the top.
C goes on top.
He goes in
And the left.
Okay? I want you to calculate the velocities of each one of these. Velocities, right there.
Oh, so we're in the ground. The Bible is 3.00 times 10.
Yes.
Mr. Household,
Yeah.
what's the unit for N?
What is the unit for N? Good question. Anyone know?
the unit for what?
Second?
N.
N would be, don't say anything. Cubic.
Remember, it's a relationship between how dense, how much an object speeds down, or slows down.
Second?
Because it's versus, yeah, 300 second, meter second, so it's a ratio. So it's negative.
So it's me.
See you guys tomorrow.
Did you just call